Different link.
Good morning, Lina. Good morning.
Good morning.
Yeah, thank you. Thank you for changing the room. Virtual room.
Good morning, Professor.
Good morning, Kia. Nice seeing you.
Oh my God.
And thanks, Boston, for establishing communications. Oh, Stephen is here. Hello, Stephen.
What happened with your previous link?
Yes, I'm suffering of it too because I was scheduling them in a scattered way. They took each day as a separate, as a different, independent link. So I did send the notes for this meeting, and for the first 20 slides, I just show steps which we did in the lab, and also I show hand-drawn models that you may consider to start building. So the homework will be a little bit later, not for Tuesday, but if you start ahead, you will save time later. So I'll show slides later, but better we talk more informally first. So in the lab 4, we did titanium hydroxide, which has 1 titanium and 4 oxygen. And if any of you are thinking about research in polymer science, or I believe everyone through general education, you are familiar with concept of polymers, right? When the same building block is repeated again and again. So polymers can be done both in the organic fashion, like biopolymers, some plastics. Same, most of the solids can be considered as inorganic polymers with repeating units repeated. So what I suggest to build a polymer of titanium dioxide, linear polymer. So taking this 1 titanium and 4 oxygen as a first model, second model with 2 titanium and appropriate oxygens, then 3, 4, and make a progression. And the next homework will be an invitation to compute total energy, homo-LUMO gap, affinity, ionization, and see how these observables depend on the length of this oligomer. So this is just a little heads up to practical aspects. And for the lecture, we are starting a new chapter. And I think I need to make a scan and share. I used this book, and I'll probably scan and share. If you do not like reading books, nothing is requested. Nothing is.
I love to read books. Me.
Huh?
I love to read books.
Oh, okay, okay. I'll share the title. And for the course, I'm not using this single book. I'm just taking a couple of lectures from one source, couple of lectures from another one. But right now we are starting actual computational chemistry in narrow sense. We will be focusing on solving electronic equation only, without motion of nuclei, and we will focus on Hartree-Fock theory that you already know how to run in Gaussian. So this subject will take about 5 lectures, and there will be several logical components. I know that if any of us need to make a conference presentation or seminar presentation in public, one can squeeze a lot of things together. So one can deliver the theory in 10 minutes. But then some internal logical connections will be missed. So I will tell this short story in a long way, for a little shorter than a month. And there will be several logical units, like Tinker Toys, Lego. So we will accumulate this building blocks for maybe 4 lectures, and then we will assemble the whole theory together. And today I will chat and show slides about the subject that you may be very much familiar, but I will look on it from different angles. So, Pauli exclusion principle, right? It's something you're aware that electrons cannot occupy the same state. And in parallel with Pauli exclusion principle, there is a requirement to a wave function, so-called anti-symmetry principle. And I'm not putting on doubt your awareness of the subject, but in order for us to use the same notations, to stay on the same page, I will revisit the subjects and provide logical connections so that later we can connect it to other parts of the Hartree-Fock theory. Any questions or suggestions at this point? Okay. Just make it on the whole screen so that I can make little. Oh, no, it's a wrong thing. Yes. Okay, good enough. So I'll skip this slides from the lab, and what we are going to cover, what we are going to get, will be related to the name of John Slater, who his name is given to several concepts in physical chemistry, computational chemistry, and my closest connection to him is that although we didn't have much overlap in time, but but when I was at the postdoctoral internship at the University of Florida, across my office there was a aquarelle, the painting that he did at his free time, because he was at the same school before. Probably I should have taken photo of it, but I didn't. So what we did up to now, so we considered the concept of ions as of molecules as ions and electrons, did set up molecular Hamiltonian, and then immediately chopped molecular Schrödinger equation onto two parts, the electronic part and nuclear part. And for nuclear part, we made Ehrenfest approximation, but for electronic, which is here, it is something we will focus right now. So kinetic energy of electrons, electron-electron repulsion, and electron-nuclear attraction, time-independent Schrödinger equation. And just as what you did in the homeworks was browsing through potential energy surface, and this concept of browsing through potential energy surface in order to find the minimum is not a material that we can pass and forget. It will be used in next chapters, and let me give a little heads up. The idea of changing some parameters in order to minimize energy is quite universal. And even if you go away from real space Cartesian coordinates, if you will go into Hartree-Fock theory, like in about 2-3 weeks from now, you will see that Hartree-Fock theory is very similar to this picture. We will modify some parameters of electronic wave function until minimum of energy is achieved. So there will be some philosophical connection. I'm very happy to get your homeworks. Thank you for your hard work. And I really appreciate that some of you converted it from PowerPoint table to real Excel spreadsheet. I think
Because
it was,
you said that you wrote it there that you we need to complete the assignment using Excel. That's it.
it was great. It was great. Thank you. And here's the algorithm that we practiced. But why do I show so many slides? Maybe I don't. So molecular Hamiltonian has 5 types of terms, 2 kinetic and 3 potential. And now we cross through and remove the things related to nuclei. So nuclear kinetic and nuclear potential energy, nuclear repulsion. And then we have three parts, 3 terms in the Hamiltonian. So kinetic energy for electrons, electron repulsion, electron to nuclear attraction. So one of the ways to solve this equation, I'm going to give an example which will be predominantly wrong and inefficient. But if you follow the train of thoughts, maybe it will help to appreciate and understand why we need actual hard-box theory. So suppose we have one-dimensional wave function, which is immediately wrong. Even for hydrogen atoms, is 3-dimensional. But suppose we have only one dimension. Then a way to find minimal energy of ground state, can be formulated in the following crazy way. So I'm doing it only as an example. So you draw the function as a set of points, as a set of grid points, and try to arbitrarily modify the value of a function at each grid point. So you just design function, and for each randomly selected function, you compute the energy and put it in a table. Then through random number generator, one creates another function, computes energy, and puts it in a table. And then by making many examples, one makes a table, puts it probably again in Excel, and sort it in order to find the minimal energy, right? So wave function is some distribution in space. We can try different distributions and select the one that gives minimal energy without any stimulus or with minimal effort. In a couple of next slides, I'm going to show why this idea is stupid, why my idea is stupid. So suppose I'm doing numerical approach and I assign only 10 grid points for 1 degree of freedom, which means I will vary 10 numbers by random numbers to represent a wave function, like from 1 to 10. Okay? Let me know if it already sounds crazy. No?
Sir, why you draw this graph? No grid. What? No grid for
10 grid points.
okay, 10 grid point. Yeah. And
10
then
grid points. So from 1 to 10. And then wave function is represented as set of points connected to each other.
Professor Kirin?
Yes?
Sorry, please can you repeat I'm sorry, please can you repeat yourself, like what we're trying to do with these 10 grid points thing? I'm sort of
Yes, sure. Thank you. So we are looking for wave function as function of position. So it is unknown function. And we can chop the whole area of definition of the function. So supposing we at infinity it will be nothing. So we need to focus on a certain range. And we represent, instead of looking on a continuous function as we do in math, in calculus, we represent a function as a set of values at grid points. Like we can put distance equal 0, delta r, 2 delta r, and so forth. And then at each value, we will randomly assign wave function being higher or bigger. So we create a function, and then just to guide the eye, we can connect it by lines. So suppose our wave function has this arbitrary shape, and for such function we can compute the total energy of this, let's say, function 1. Then we can repeat this procedure and do another set of random numbers, make another function, another random function. Let's call it phi2. Energy of phi2. And then we can do it like 1,000 times or whatever we need. So if you have a set of such random functions and set of energies, we can just order this list of energies and find the one that gives minimal energy. And there is a principle: the one that gives minimal energy will be most probably realized in nature.
Sorry?
The one
minimum energy gives
minimal energy.
Okay.
So okay with this?
Yep.
Okay. Now I'm going to show why it is not as reasonable. So actual wave function depends on multiple, as many vectors, as many electrons are in the molecule. And each electron has three Cartesian projections, x, y, and z. So R1 should be understood as x1, y1, and z1. So if you have n electrons, then we have 3 times n electrons degrees of freedom. Now, if I still want to practice this random number generator for wave functions, then for single hydrogen atom, and I use only 10 grid points per degree of freedom, then for hydrogen atom, I will need 10 to the third power, because each dimension is independent. And if I have 10 grid points for x, 10 grid points for y, and 10 grid points for z, then the total number of grid points I need to represent wave function will be 1,000, right? If I focus on molecular hydrogen, H2, with 2 electrons, then it will be 10 to the 6th, right? Because if you x1, x2, y1, y2, z1, z2, 6 degrees of freedom, 10 to the 6th grid points. if I want to describe single carbon atoms, it has 6 electrons, so it will be 10 to the number 18 grid points to represent wave function. If I'm going to one of the simplest organic molecules, acetylene, so 6 electrons per carbon, 2 electrons, 1 electron per hydrogen, total will be 14. So, and 3 Cartesian projections for each electron, so 10 to the power 42. By today, it's about a limit of computational facilities. So if we use this approach, we will not be able to describe molecules more complicated than acetylene. So something is wrong with this idea. We need to, we cannot do it just because of the numerical limitation. So we need to do some tricks, to do some approximations to get away from this challenge. So when there are too many degrees of freedom, typical way is factorize the function, right? If the function depends on many degrees of freedom, one function of many variables, the mathematical approach of separating variables will be to represent one function of many variables as product of many functions of one variable, right? Phi 1 of R1 times phi 2 of R2 times phi 3 of R3. So if we would be able to tell that wave function of all electrons is a product of the wave functions of each individual electron, then we could solve for individual one electronic wave functions, then combine them together and find the overall solution. Make sense? Okay. So the factorization is possible if the operator in the differential equation has additive form, if contributions if the set of terms in this operator can be represented as summation of operators acting on one variable only. I'll better just write it by words. Separation is okay if operator is a sum of operators acting on individual degrees of freedom. Individual electrons, or individual degrees of freedom. So it would be an ideal world where such statement is possible. But unfortunately, for mathematicians or for us who are trying to address this question, the operator includes electron-electron interaction. So this term, which is summation of charge, summation of distance between electron number I and electron number J. So this summation over I and J. So this term does not act on a single electron, and therefore it precludes us from immediate practicing of separation of variables. So in some sense, it is a bad guy who prevents us from efficient solution. So we need to design a strategy to get away from this situation. So here is the plan. Let's first build a very approximate wrong solution that does neglect electron-electron interaction, compose many electron wave function as we would do in the ideal world, and then design the way to include electron-electron repulsion in there. So we do not have chance to retreat, withdraw, surrender. We need to go this path, and at least we will try to do simple things first, and then design more advanced, complicated ones. So we will try to discuss if one can construct multi-electron wave function as a product of single electron function. And I show a photograph of Dr. Mikhailov here because when I was teaching this course for the first time, he was substituting me, and he made a couple of slides for it, so I keep appreciating it. So here is the electronic Hamiltonian. This is kinetic energy of electrons. This is potential of between nuclei and electrons, and this is electron-electron repulsion. So if we remove electron-electron repulsion, and if you have only one electron, then you will have only the first two terms, and one ion and one electron, and it will be hydrogen atom. And for hydrogen atom, there is a known set of solutions that those of us who were or will take advanced quantum mechanics are aware or will be aware soon. So for the hydrogen atom, the solution of one electron function has this highlighted shape. So product of radial component and angular component, and there are explicit mathematical expressions. Of course, we are not in the math class. We are not going to write this equation for again and again. They all are encoded in the programs that we are doing, but answers are available through special functions, through special polynomials. There is a solution for radial function. There is a solution for angular dependence, and in the simplest way, this angular dependence includes angular momentum. The quicker rotation of electron around nuclei, the more fringes are on this path. And here you may recognize some images that are part of the freshman chemistry. So let me know if you recognize these images or if you don't. So who is Steven? What are these images? Can you tell by in a simple words?
They represent probabilities of finding either singular or pairs of electron around a nucleus, and this is inverted from the way that they're typically shown in a general chemistry textbook, which would have the S at the bottom and the F at the top, representing their total energy levels of the electrons.
Okay, thank you. Anyone wants to add anything to this discussion, or everyone agrees with Stephen? I think everyone agrees. Yeah, thank you, Stephen. So the hydrogen wave function has 3 quantum numbers, actually 4: principal, orbital, magnetic, and later on spin. And the orbital and magnetic determine the shape of the one electron orbital in space. So if there is no orbital angular momentum, it will be symmetric as function of angle. If it has the minimal non-zero value, it will be p orbital, which can be oriented x, y, and z. And then there are more complicated shapes where orbital quantum number tells about overall number of fringes, and magnetic quantum number tells how fringes are arranged in the plane perpendicular to z-axis. So if you look on the f orbitals, which are more complicated, but trend is seen better. So if magnetic number is minimal or maximal, we have a lot of fringes of this green and red correspond to positive and negative. And as we go across the circumference, it changes sign, plus, minus, plus, minus. If magnetic number is 0, then as we go across the circumference, the sign is not changing. Okay? So it basically matches expectation. And for radial distribution, the s orbital is localized closer to the center of atom. The lowest s orbital. Then the second s orbital has a dip, so it has maximum near the center and then second maximum. And the p orbital has 0 near the atom and a maximum away from it. So if I jump back, here is an example of p orbital, and in the place where ion is located, the value of the wave function is 0 in the center. And as we go away from it, it increases. Just for p orbital. Let me open a browser and encourage everyone right now, simultaneously with myself, to look onto web site that is named ptable. ptable, I think, .com. So I will do it myself, but you are please go ahead and try to navigate and look on it. So this is a really useful tool, and there Yes. So it's more educational table that shows properties of elements, and if we select the tab electrons, then it does show the Aufbau composition of each element. Like the titanium, let's start what we did. Carbon will be, if you look into the area that I'm navigating with the mouse, so it shows 1s, 2 electrons, 2s, 2 electrons, 2p, 2 electrons, total 6 electrons. Right? And if we would be not in a graduate school, but in high school or freshman chemistry, this table would help to do some homeworks, to feel Aufbau principles of element. Just go and copy paste from it. So go from some advanced element, and it shows how the electrons feel the cells of this quantum state. But what is, for example, titanium that we considered in the lab? So in addition to this central area that shows Aufbau, the occupation of quantum states by electrons, there is another area of this tool. So please have a look on the lower left of this thing. So you see this colorful bubbles, right? Do you? And here is a, if you never saw this website, let me show a hocus pocus. So if I click on different cell here, the image changes, right? And if I click on 1s orbital, it shows just this sphere. If I click on the 2s orbital, it shows that there is a change of sign as we go. If I click on the p, it shows this dumbbell shape, which is oriented in different orientations. And if I click on the d orbitals, it will show the stuff that we already considered in the table. So the minimal and maximal values show several changes of the sign along the circumference. And if we take maybe something that has F elements, some of the lanthanides, we can click on this F quantum states of electrons that has a larger value of angular momentum. And as we go across, the minimal and maximal values have change of the sign, has swap between this red and blue colors as we go across the circumference. If you click in the center, it will be nothing changes as we travel along in the XY plane. Make sense? Okay, so I hope you enjoy this this table, and let me return back to the slides. So the meaning of atomic wave functions centered at positive ions, that they will serve as a minimalistic building blocks to formulate multi-electron wave function for a mole. Right now, we do not know how to take into account electron-electron interaction, but we will solve it later. Let's look for some other possible mistakes that we want to avoid. So there is a concept that I was not able to get in my undergraduate studies and even at the beginning of graduate studies. It's maybe I knew how to answer on exam, but it's something that doesn't exist in our everyday regular world. So if you feel a little discomfort with this concept, do not feel do not feel that it is strange. So I'll try my best to explain. On one hand, we have Pauli exclusion principle, that there are no, in a given object, in a given atom or given molecule, there are no two electrons that have the same quantum number, same quantum state. So if we translate, and we use Pauli exclusion principle for this Aufbau principle, but if we translate this principle into wave functions, into procedure of composing multi-electron wave function out of single electron wave function, there will be very special requirement how to build a multi-electronic wave functions out of single electron wave function. And the name for this principle is anti-symmetry. So the interpretation of this anti-symmetry that I plan to finish in 12 minutes is that if first we need to formulate and follow anti-symmetry principle. I didn't introduce it, but we will do it in a few minutes. And if we try to violate this anti-symmetry principle, it will be something unphysical that nature will not accept. If you try to construct wave function that doesn't follow anti-symmetry principle, it will be not realistic. What does it mean non-realistic? It means that it will include close proximity of electrons that will repel each other so strongly that energy of this wrongly constructed wave function will be too high, will be unrealistically high. So when I was in the undergraduate studies, I was I didn't like the words of my instructors about principle that wave functions must obey, because like it should be democracy. Wave function should take any shape it likes. And yes, it can take shape that doesn't follow anti-symmetry principle, but then the energy will be unacceptably high. Therefore, it doesn't happen in nature. So here, I'll show better slides. Those are ugly hand drawings. Here are a little better hand drawings. So slowly but surely, let's formulate it. Suppose that we have only 2 electrons in the system. Then wave function depends on the position of first electron and second electron. So the principle that is a main part of today's meeting is that if we swap the order of electrons, then the wave function should keep the same shape but change its sign. So if we take wave function absolute value squared, which will be probability distribution multidimensional, and if we swap the order of the electrons, it should be the same. So if we have first and second, and here we have opposite second and first, their absolute value squared should be the same. So the sign of the wave function changes, but the shape does not. we have to believe and accept that this principle will enforce any wave function to obey power exclusion principle. We should believe, and I plan to show it in the next slide, that if someone constructs a wave function that does not follow this principle, then it will be something unreasonable. So suppose we want to violate Pauli exclusion principle, and we will place first and second electron into the same quantum state, into the quantum state that is labeled by the same orbital. So instead of 2, it will be 1. 1, 1, and 1. And we will have first electron in state 1 and second electron in state 1. And then we will practice this anti-symmetry form that I suggest here. And by following this functional form, we will get 0 if we were trying to place 2 electrons into the same state. So let me ask you to try to verbalize this principle yourself, because I feel that I didn't made a good job in telling you. Lina, would you like to try?
So here we have
I can open new slide and rewrite the equations a little better. But if you are not sure, do not worry. Boston, would you like to try?
Yeah. So, what are you asking me to explain again?
I'm asking you to explain why the antisymmetric wave function is expressed as a subtraction of 2 products.
I'm not sure
Good.
myself.
Do not worry. Do not worry. I'll try to do it over so that we all are on the same page. And do not worry if something goes slower than planned. Main part of the course is practical thing, and I'll make sure that these building blocks are accepted and everyone understands. So do not worry. This is not theoretical course. We just need some concepts before we go forward. So here is, I would say, a theorem. So if we have 2 one-electronic functions, phi 1 and phi 2. So 1 and 2 means here set of quantum states. For example, principal, orbital, magnetic, spin. So I just do not want to be specific right now. So for these wave functions, we are going to place 2 electrons. First electron and second electron. So out of these 2 wave functions, I need to construct multi-electron wave functions. In this case, 2 electron wave functions. Big letter phi that depends on R1 and R2. And this wave function must obey the principle of phi R1 R2 equals minus phi of R2 R1. Please confirm if it is clear up to now. Okay, and do not
Yeah.
hesitate to stop me if something goes unclear. Now, here is I would say a theorem or statement. In literature, people do not call it theorem, but it's just principle. So, in order to obey this principle, wave function, multi-electron wave function is constructed. 1 R2 as small phi number one electronic function for electron 1, small phi state 2 for electron 2, minus small phi state 2 electron 1, small phi number 1 electron number 2. So if we look onto this expression, then we can notice that electrons are swapped. So in the first term, the indices coincide, and in the second term, indices do not coincide, right? And there is a convenience to put normalization factor up front, 1 over the square root of 2 for 2 electrons. So this functional form of constructing multi-electron function, wave function, out of single electron wave function must be obeyed at all times. And the, I wouldn't say proof, but demonstration that this is a really good functional form is that if we try to violate, Pauli exclusion principle, try to violate Pauli exclusion principle. So what if we try to put, so we have two quantum states, 1 and quantum state 2. And now we have two electrons, 1 and 2. So if we will put both electrons into one quantum state, so our functional form should prevent us from doing this mistake. Both electrons in one state. I'm going to copy paste this slide and then just change something quickly. So if I want to put two electrons into one state, means here instead of 2, thank you, and here instead of 2, I will put 1. So it will be wave function 1, wave function 1. And now we have 1 everywhere. Here, there, right? You see. But electrons are different. First, second, first, second. So what will be the answer? Just show, look here, phi 1 R1, phi 1 R2, minus phi 1 R1, phi 1 R2. What will be the answer?
0.
Yes, thank you. 0, which means such wave function does not exist. Which means we did something wrong. So this functional form prevents us from constructing wrong wave functions. If you do something wrong, it will just disable the whole, ruin the whole answer, and it will be a signal that we did something wrong. It is, I do not reproduce how people arrive to this functional form. I'm only, how to say, defending it.
Okay.
But if we do not make wave functions to follow this functional form, then we will not get the correct multi-electron wave function.
Okay.
So and I just provided a little demonstration that this functional form helps us to avoid wrong wave functions.
And Professor, what about this figure, the above figure, and that one, phi 1, then phi 2, then you draw that figure. You just draw this. Yeah. Can you just explain it within 1 minute? I know it's already 10:09, but just explain it.
Yeah, I'm fine. So there are two functions.
Yeah.
Two quantum states.
Yes.
And I'm going to put electron number 1 and electron number 2 into this state.
Yeah.
So if I want to put electron number 1 into state 1, I will write here R1.
Okay.
But if I want to put electron number 2 into state 1, I will write R2. Make sense?
Yes. And Professor, it's a theorem. We don't need to derive the theorem. We just need the physical meaning of that theorem, right? So what's the name of that theorem? I just saw this one for the first time. For the first time I saw this one.
So the concept, if you want to look in other sources,
okay,
look for anti-symmetry of wave function and Slater determinant. So the best keyword to find it is Slater determinant. Slater determinant. Make sense?
Yeah. Later determine.
Slater determinant.
Slater determinant.
So it's letter letter R. Determinant. And here is the letter N.
Okay.
Determinant.
Okay. Okay, Professor.
So this functional form prevents us from constructing wrong wave functions. If you do something wrong, it will just disable the whole, ruin the whole answer, and it will be a signal that we did something wrong. Okay? Boston, do you agree?
Yes.
Okay. So I was trying to put my load on your shoulders and ask you to explain something like this. Sorry about this. I believe it's time to end. Let me quickly just skim through slides, but I will repeat them when we meet next time. So here is this principle. It can be one is getting this functional form by placing one electron wave functions into 2x2 matrix and taking determinant. So if one will practice this determinant, one will get exactly what we discussed. And if some people hate words, some people hate equations, but some people really love pictures. So let me show how this will be represented in a graphical form. And I'm over time, but I will finish in maybe 3 minutes. There will be no new information, no illustration. So if phi 1 is sine x and phi 2 is sine 2x, we want to practice, we want to place two electrons, compose two electronic wave functions so that it will be electron 1 and electron 2. 2. So sine x has one hump. Sine 2x has minimum and maximum, right? So along x1, we have, as we go forward, we have green corresponds to 0, then it grows, and then it goes back. Along x2, we have positive, and then it goes to negative. And as a product, we have two blobs. One is yellow for plus, one is blue for minus. Okay? Now, if you swap, if you keep the same orbital, same coordinates, but we swap the order of functions, then this maximum and minimum will be aligned not along x2, but along x1. Make sense? So plus, plus and minus. Now, if we subtract these two wave functions, then the plus and minus will be aligned not along one axis, but along anti-diagonal. Plus and minus. So it is a visual representation how the anti-symmetry wave function should look in the simplest possible case. So it's not possible to see it as a function of 1 or 2. It's a really two-dimensional thing. And if we swap x1 and x2, then the plus and minus changes its position. So it by swapping x1 and x2, it will be just change of the sign of the wave function. So I think it is enough for today. Thank you much for your patience and dedication to the class. Wishing you to have a relaxing weekend and maybe a little warmer weather. And looking forward to see you next week.
Have a good weekend, everybody.
Thank you. Have a good weekend.
So meeting is done. I'll stay here if any questions appear, but everyone is welcome to disconnect.
Okay, thank you.
Okay, thanks. Have a nice weekend all. Bye.
Oh, thank you, Lina.